All right. Thanks for joining us this morning. As people are popping in, I'll just do a little bit of webinar introduction, and then we'll get started with our presenters. All right. So thanks for joining today's Research Radar webinar, Sustainable Transportation Solutions, hosted by MnDOT and the local Road Research Board. My name is Jackie Duran. We're excited to have our presenters today, Dan Gullickson, Elliot McFadden, and Rachel Pickelman joining us. Today's webinar is the third in our new Research Radar series. Each month, we will highlight 3 research projects focused on a common theme. Last month, we featured three research projects on autonomous vehicle innovation. MnDOT's Office of Research and Innovation manages more than 185 research projects in progress, ranging from local initiatives to pool fund projects with other states, comprising both basic and applied research. We're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your needs. Recommend the best research methodology for your project, access local and national funding sources, and manage your project from start to finish. The Local Road Research Board is a city and county-run organization that sponsors research and educational initiatives that address local transportation needs. You can stay up to date with our research by following us online and subscribing to our newsletters. We will send you website and subscription links in a follow-up email after this webinar. We're excited to announce the funding of 27 new academic research projects selected from a competitive pool of 82 proposals. To see the full list of new projects, you can scan this QR code on your screen. And if you have subject matter expertise on any of these topics, we would love to have you reach out about serving on a technical advisory panel. Have a new idea or a problem that needs solving? We're accepting new ideas on Idea Scale through April 1st, and you can also scan this QR code to access that. So unique to today, we're also requesting ideas from you for near-term, quick turnaround, sustainable transportation research. Ideas should respond to those near-term needs or emerging issues within the selected project beginning in the summer of 2025. So ideas should have a specific focus with project durations of less than a year for quick turnaround research results. And this is a pilot partnership between MnDOT and the University of Minnesota. So before we get started, I will read the Tennyson warning. This session will be recorded for those who cannot attend. If you've enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You're not required to allow MnDOT to use your image, and there are no consequences for declining to do so. So to opt out of the recording, simply turn off your camera. All right, I'd like to now introduce our presenters. Dan Gullickson is a University of Minnesota forestry graduate with over 30 years of experience working with public and private landowners, installing windbreaks, shelter belts, and snow fences to better manage blowing and drifting snow. Dan is the Blowing Snow Control Shared Services Supervisor with the Minnesota Department of Transportation. Elliot McFadden is the interim supervisor of the Mobility Management Unit in MnDOT's Office of Transit and Active Transportation, where he oversees the state's shared mobility program, federal transit funds for services for seniors and people with disability, and management of the ABC ramps, a multimodal parking and transit facility in downtown Minneapolis. In his previous role as MnDOT's Greater Minnesota Shared Mobility Coordinator, where he led efforts to pilot and scale shared mobility services with public transit partners in rural, tribal, and small urban communities, including establishing the state's Shared Mobility Innovation Program, Moving Greater Minnesota Forward, and launching MnDOT's award-winning Regional Mobility as a Service project, a multimodal trip planning, booking, and payment platform. Rachel Pickelman serves as the hydraulic resiliency engineer for MnDOT, working within the hydraulics unit and in the Office of Bridges and Structures. In this role, she is responsible for leading efforts to improve the flood resilience of MnDOT's infrastructure by developing design guidance, participating in research projects, providing expertise for flood mitigation projects, and conducting internal and external collaboration to share knowledge. We will have time for questions after the speakers present, so please enter them in the chat box throughout the presentations. And now I'll hand it over to Dan Gullickson to discuss harnessing solar energy through solar snow fences. Go ahead, Dan.
You see my screen?
Sure do.
All right, excellent. Well, thanks everyone. Glad to be here today to share our research project with North Dakota State University, talking about using solar snow fences to collect energy from the sun and also help us control blowing and drifting snow. The picture that I have before you here is showing the solar snow fence section here with the solar panels on, adjacent to one of our flexible composite rail snow fences, which is our traditional type of snow fence that we use with the brown snow fence. I want to acknowledge and thank the research office here for helping fund this research implementation project. It's a $227,000 research project. It's been going on since June 30th of 2022, and we will wrap this project up in 25 here on June 30th. North Dakota State University is leading this research effort, and Dr. Mija Yang and his team there we're very much indebted to them, because without them we wouldn't have the benefit of getting this data collected in the field. So the intent here, you'll see some of the North Dakota State slides in here with my slide set. The intent here is to have a multi-purpose function here. And so with snow fencing, they're up year round. Why not have the opportunities to create energy from them that can be used? That could also maybe help offset the cost of installing these snow fences. Our traditional type of snow fence, a living snow fence, is running about $400,000 per mile to install. And our traditional type of structural snow fence is running around $580,000 per mile to install. So these are sizable investments that if we could potentially offset that initial cost by producing energy from them is what we're trying to learn with this research project. And then looking at also helping reduce our carbon footprint in terms of snow and ice removal. We know where we've deployed our living and structural snow fencing in areas of the state, we've been able to reduce the need to go out there with the tractors and blowers and the extra equipment to regain that pavement and do post-storm cleanup. And so maintaining that type of efficiency along the way. Now, as we look at our solar snow fences, we want to make sure that they also function as a snow fence. So as part of the research project, the North Dakota State folks are going out there and measuring the drift profile. Here we have our solar snow fence. It has a porosity of about 38%. So it's got a little more density than our traditional snow fence, which has 50% porosity. So that does cause the snowdrift profile to be a little bit different. But at the end of the day, we want to have an understanding of that so that we can properly site these things in the field. To give you a feel for where the snow fence is located, it's located in MnDOT District 4 off US Highway 10. And the prevailing wind directions with the black arrow there, it's coming across a mile plus across the farm fields. So we've got a really good test section here for assessing its effectiveness. The snow fence installation here is using a different type of method of installation. They're using helix foundation, which basically gets screwed into the ground. And then when they hit resistance, they know when they can stop, that they have enough resistance there to hold the structure. But they can keep adding these extensions here until they hit that point of resistance. So it's an innovative way of installing it. These foundations are in the ground about 6 feet, and this is the post that goes into the sleeve, and then you can see the posts that are located here before they start to assemble the solar panels. It's an 8-foot tall system, and the solar panels have a metal backing to give them support. They were finding that they weren't going to have enough strength in the solar panel if they did not put the backing on there. And so they were able to test that in the lab at North Dakota State. And then we've had it out in the field now for 2 years to assess its effectiveness in terms of holding up to the wind loads. And it's working really, really quite well for us. So what is the energy production of this solar snow fence? We have a 100-foot section that was constructed, and they are collecting monthly and daily data in terms of its energy production. And so on average, we're producing 11 kilowatt hours per day with this 100-foot section of snow fence. As we look at our year, the months that are, the colder months like November, December, January, February, we're all pretty much right above that 10 kilowatt hours per day with that, and that's with the lower sun angle. So that's encouraging. You'll see an outlier here. Their cell phone plan wasn't renewed on time, so we're missing data for the month of August. So that's why we see the month of August at such a low level there. But that's the beauty of research is, you can have these little hiccups there and it's not an end all, it's just part of the learning curve. So the way the system works, the system is not connected into the grid at all. Everything that's being produced by the snow fence is being used on site. And so the energy that's being collected is running through these cables and going to the storage cabinet. Inside the storage cabinet, we have our battery system, the inverter, and the controller for managing the system. There's also heated pads around it here. And then they have weather instrumentation, little lighting here, just having opportunities to utilize some of that energy that's being produced since we're not in the grid. So as you look at the solar snow fence, the solar panels are collecting the energy from the sun in a direct current. And so then it needs to go through an inverter and gets so it can be put into an alternating current that can be used by your appliances out there or to be connected up to the grid. So they had to come up with the electronics here to be able to convert the power. And a lot of innovation here was done by North Dakota State. It uses a solid state transformer to read the sensor outputs from the main module to prevent unstable operation. The entire system can be disabled in the event of an emergency. Modules are isolated, so a problem with one does not affect the entire chain. And then due to the high frequency isolation transformer design inside each inverter module, only low voltage DC current of 30 to 50 volts and low voltage alternating current 36 volts are generated within each module. This is really an important piece here in order to prevent accidental electrocution. Even if the solar system is hit, someone goes up to it and hits it by accident or in the form of a crash, we don't want to see people get electrocuted. And so by managing the system here, we can make it safer and have it in areas where people could be around. So as I mentioned, the energy is being used in these heating pads. After the snowfall here, you can see this, the heating pads are covered and then later in the day, the snow is melted. And this is kind of an active system in the sense that it's not only just a snow fence, but it's also actively melting the snow around the snow fence throughout the winter. And that can have some benefits in the sense of reducing our offset from the road with these snow fences because they're continually melting snow. We also have a webcam out there. And so we're trying to find opportunities to utilize that power on site that's being generated. So one of the things that the research team from North Dakota State looks at is kind of the economics of this. And so as part of their economics benefit cost, they found that a power purchase agreement model is a mechanism that would allow MnDOT to accrue the benefits of the solar power without owning the system. In a power purchase agreement, a developer procures, builds, operates, and maintains the system, while MnDOT may buy the power from the developer at a negotiated rate. And thus the developer builds the system, MnDOT would benefit it and also be purchasing it at a negotiated rate. And there's various solar developers that are out there, and there's probably more that'll be coming on board here. So with the power purchase agreement, the benefits to MnDOT are it is minimal upfront capital costs, lower energy costs potentially for our system, and then there's no system upkeep because it's being done by others. So let's take it from the lab here and from the field, and let's talk about how we could potentially utilize this in a real life scenario. And the example I'm going to share with you has not been constructed, but I just want to share with you the potential. And that is, what if we were to take a highway rest area and heat the concrete in the plaza so that we're not having Greenview out there shoveling as frequently, helping with that safety getting into the rest area? What would it take to keep the lights on in the rest area with the solar snow fence? Well, for this to work, we need to be interconnected into the larger electric grid. We'd have to work with the local electric company there to get the approval to make sure that it's safe for their people, as well as they're having a consistent flow of electricity from our system. And then MnDOT or a power purchase agreement developer would need to install the electrical system and interface with a licensed electrician, and then it would all have to be approved by the electric utility. So looking at that scenario there, we've got 6,000 square feet that would need to be melted in terms of sidewalk and plaza to get up to the rest area building from the parking lot. North Dakota State looked at, well, what does it take to melt 2 inches of snow? It takes about 14.4 BTUs per square foot to be able to melt that snow. And so as we look at the number of BTUs needed to melt 6,000 square feet of sidewalk and plaza, that's over 100,000 BTUs. 1 kilowatt hour is the equivalent of 3,412 BTUs. And so you look at the number of BTUs divided by that 3,412, it converts it into, we need to be having the ability to produce 29.81 kilowatt hours per day. Now with the concrete's not is going to only probably be 80% efficient in terms of transferring that energy. And so we need to factor that in. So with that, we need to bump that up to about 37.26 kilowatt hours per day. We know that the 100 lineal foot of snow fence is 11.7 kilowatt hours. So taking that 37.26 divided by the 11.27, we need about 318 feet of snow fence to be able to keep that sidewalk plaza melted. And some of the other research that we're seeing, like from other universities, like Iowa State, looking at having heated pavements, having the 6-inch base, having 2 inches of styrofoam insulation, but near that base, putting in your concrete that has a carbon fiber 2% by volume content helps to move that energy from the heating grid that would be embedded into that concrete. And so this would be just a hypothetical scenario, but could have some real life applications in terms of just making it safer to get into a rest area building. What if we were to keep the lights on? Well, you can, reaching out to the utility company, they looked at our energy use in 2023 using 33,480 kilowatt hours of energy, which figures out to be about 91 kilowatt hours per day. In 2024, the numbers are fairly similar. The peak demand was 10.2 kilowatt hours. And so looking at the ability to keep the lights on, we would need 780 feet of snow fence to be able to keep the lights on in that facility. And so if we want to keep the lights on and keep the snow melted on the sidewalk and the plaza, we would need about 1,100 feet of snow fence to be able to meet that demand at that rest area. So summary and conclusion, the solar snow fencing system has been designed, built, and installed in the field. We haven't implemented something like I described here, like at that rest area scenario, but we have developed a 100-foot section to test to see what it can produce. And the performance has been monitored over the past 12 months. Our average energy generated averages between 10 to 30 kilowatt hours, depending upon the solar intensity of the day. Electricity generated has been used by 16 melting pads, which makes this system an active system that it's not only a snow fence, but it's also actively melting snow throughout the winter. And all the electrical, the monitoring system, the data for the snow melting can all be controlled remotely. All these systems are powered by the solar energy being generated. And NDSU believes that the power purchase agreement route is the best approach for implementing the system, and that there still can be some efficiencies gained in terms of maybe having longer solar strips, fewer posts that could increase our payback. Right now, they estimate that payback return can be anywhere from about 5 years to 11 years with this type of a system that they've developed, but there could be further efficiencies gained with further refinement. I've also reached out to the Department of Administration, Office of Enterprise Sustainability, to get their thoughts on the solar snow fence. And their thoughts are that the amount of solar energy being produced by this is less than 2 to 10 megawatts, may not garner much interest from solar developers. This 1,100 feet that I mentioned that we were doing this hypothetical, that would have produced about 0.13 megawatts. So may not attract much interest from these larger developers. The solar snow fence is a specialized custom build application that could scare away some developers. NDSU had to fabricate those solar panels so they're 6 inches wide, getting them to fit on the rails. That's not your typical solar panel. They're usually much larger. And so there might be some challenges associated with that. But all in all, they consider this to be an exciting concept with potential benefits, even if MnDOT does not connect to the solar snow fence into the grid. Like, for example, if we were to maybe just heat the concrete, heat the surface so that maybe bridge decks aren't frosted up as frequently, or helping with sidewalks and that type of thing. So anyway, there seems to be interest from the Office of Sustainability within Department of Admin in this concept. And with that, I thank you.
Thanks, Dan. Appreciate that. It's been a really fun implementation project to follow. So we really appreciate your time. Next up is Elliot McFadden. He's going to share about impacts of shared mobility on infrastructure usage, greenhouse gas emissions, and accessibility.
Yes, thank you for having me. Let me make sure I'm to the right window. So I'm going to be presenting as the technical lead on our project impacts of shared mobility on infrastructure usage, greenhouse gas emissions, and accessibility. It's a very pithy name that just rolls off the tongue. I wanted to start just by defining what is shared mobility. I have previously been the manager of our statewide shared mobility program at MnDOT, but it's somewhat maybe a technical term not everyone's familiar with. So when we talk about shared mobility, it's essentially any transportation service that is shared among users. So users may use the service at the same time or independently of one another. So examples of services that are used at the same time are public transit, taxi and ride hail services, and carpooling and van pooling. And services that may be used independently are things like car share, which is akin to short-term car rental within neighborhoods, bike sharing, scooter sharing, and some types of delivery service. We've been seeing over the years as these new technologies are coming into place, lots of different impacts, lots of promise in the technology, but possibly negative impacts as well. So there's been research done that showed while there's tremendous potential for ride hail, they can make transportation worse. Car sharing has had a lot of research around being able to reduce the number of vehicles people own and reduce their number of private car trips. And bike sharing programs help get people onto green transportation, but also have operational needs to balance vehicles, move them around that may impact and offset the benefits from that as well. So some of the benefits we think about with shared mobility, as I mentioned, traffic congestion. So if we're moving people out of private vehicles, we may be looking at ways to reduce traffic congestion. It also can reduce impacts on infrastructure development, especially if you move to bikes and transit. There may be less need for additional road capacity and less wear and tear. It's also an accessibility issue. So we have many people within our communities that don't have access to private vehicles, and shared mobility is another layer on top of public transit. Private shared mobility providers can add more access, more options for folks to be able to go to appointments, be able to go to work, and just generally quality of life. Be able to access everything that someone with a personal car can. It also has tremendous potential to help us meet our greenhouse gas emission goals. So moving people to lower carbon footprint options. Also, because of the heavy use of fleet cars, it makes it easier to introduce electric vehicles into fleets at a higher rate than you would see in the private marketplace. There are some costs though as well. So we may need to look at how we design infrastructure to accommodate things like pickup and drop off zones and spaces for bike share, bikes and scooters, things like dedicated lanes, additional sidewalks, and additional accessibility. So the project that we've been working on has been trying to address the problem of how shared mobility options are changing travel behaviors. How are they impacting vehicle miles traveled, infrastructure use, and the environment? And the challenge that we have is our existing models don't really account for these new shared mobility options. So we have a harder time predicting the impact as these systems grow or policies that may be implemented to grow or reduce the number of options. And so the solution is to create a new model that looks at how different fleet sizes and different policies may impact these different goals for both at MnDOT and also for local partners. And our lead investigator on this is Michael Levin, a PhD at the University of Minnesota, who works in the Department of Civil, Environmental, and Geoengineering. Just to give you a quick overview on the budget, it's a 24-month project, $161,000. We are in the second year of the project right now. So there was some initial data collection that I'll talk about here in a second, and then developing the model and the software that will do these projections. We have already gotten into building the part of that model that's starting to look at traffic and infrastructure impact. Later on, as we get in further into the year, we'll add more accessibility measures and greenhouse gas emissions, and then looking at later this year and early next calendar year having final reports and tools that would be available for folks in the field. So just an example of some of the data collection that's already been happening using our different sources of traffic information to pull together a really comprehensive look at traffic patterns within our road network. Also looking at accessing transit data and layering that on top of it, as well as data from shared mobility providers, so that we're really getting a comprehensive look at the kinds of trips and vehicles that are being used and where they're being used across the infrastructure to help build a realistic model. The modeling approach itself, as I mentioned, brings together all of these different data sources. It's looking at how people choose to make a trip, by what mode. It assumes that users are going to try to take the travel option that provides the least amount of travel time as its primary way of looking at mode choice. And it aims to be a comprehensive model of predicting travel behavior based on different levels of fleet availability and policies that you may implement that may impact those as well. I'm going to share a sample scenario that's been run as part of the model as it's being developed right now. So in this case, we're looking at the city of Minneapolis, and we have 4 scenarios. We have a base scenario, which is the current conditions in Minneapolis. We have a scenario where we've implemented policies that make the price of using a TNC, which is a transportation network company or ride-hail service, so a service like Uber or Lyft. We've implemented a policy that makes that very high cost, so it's discouraging users from using the TNCs. The second scenario is we're looking at increasing the availability of shared electric vehicles. So if you're familiar with Our Car and the EV program, this would be what that would be. Looking at some of the impacts of that in the decrease of private vehicle uses and the increase in shared electric vehicle use. And then the final is policy, what if you removed permitting for shared scooters and bikes, and what impact that would have. So I'm just showing a couple of, on the initial modeling, the impact across these this base scenario and 3 alternative scenarios. So we can see, in this first private vehicle usage, if you're increasing the cost of TNCs, then that's going to cause more people to move into private vehicles, where if you're increasing the availability of electric shared vehicles, you're going to see a reduction in private vehicle use. The orange chart is the total system travel time. So we see when we also look at the congestion scenario that you have your base scenario, and then by reducing the number of TNCs, you are actually reducing the number of vehicles and potential what we call deadhead miles, so those miles that are happening outside of the specific trip to either get to the next trip or to get a vehicle into the field. So you're seeing a reduction potentially in congestion and travel times there, whereas as you increase the electric vehicles, you're going to get a shift in lower usage, but maybe not quite as much. And our project end goals are really to make this a tool that better informs decision makers. So as both at the state level and more specifically, a lot of policy around shared mobility is developed at the local level. Having a data-driven approach to understand what the impact of different policies would be as you increase or decrease the availability of these services, and then have a better sense of how that fits into the general landscape of overall policy goals for those organizations. And with that, I will stop now and turn it back over to our MC for our next speaker.
Thanks, Elliot. I appreciate it. Thanks for sharing that research in progress and leading that project for us. So just want to remind everybody, we are going to have just a few minutes at the end for questions. So you can go ahead and put those in the chat, or we'll prompt you at the end. So our last presenter, Rachel Pickelman, will talk about investigating real storms and the impact of potential climate change adaptations.
Thanks, Jackie. Can you see the screen okay?
Looks great.
Thank you. Great. So as Jackie mentioned, I'm going to be talking about an ongoing research project that's titled Investigating Real Storms and the Impact of Potential Climate Change Adaptations. And I do want to start by acknowledging the research team at the University of Minnesota, St. Anthony Falls Laboratory. That team is led by Andy Erickson, and I very much appreciate the work that they're doing on this. So, quick overview of the information I'm going to share. I'll start out by talking about why we are researching real storms and what exactly I mean when I say real storms. And then I'll give an overview of the research itself. And I'll conclude by talking to you about how we plan to leverage the research outcomes. So, to get started, why are we researching real storms? And there's kind of two parts to this answer. The first part has to do with the assets, the infrastructure that we have throughout the state. So many of you, especially those that are MnDOT employees, are probably very familiar with this information here. But quick overview, we have 8 districts throughout the state shown on the map in the middle. And we have a lot of infrastructure, right? We have over 11,000 miles of roads, more than 2,700 bridges over waterways, more than 70,000 culverts, almost 75,000 storm sewer pipes, and there's a lot of other assets that I'm not even listing here. And, you know, if the conditions are right, like if we get a really intense rainfall for several hours or even days, these assets can be potentially impacted by flooding. The second part of the answer has to do with trends that we're seeing in rainfall. So this is a bar chart that the State Climatology Office put together for us. And what it does is it looks at long-term weather stations in Minnesota, and it groups together the rainfall events that have been observed at these stations. So what we're showing in the legend here is we have the dark blue bars represent 10-year recurrence events. That's about a 4.5 inch rainfall event in 24 hours, and that's what we typically use to design storm sewer systems. On the other end of the spectrum, we have the dark red bars representing our 100-year rainfall events, and that's about 6 to 7 inches of rain in 24 hours. And those are the events that we typically use to design stormwater ponds. And so the takeaway here is that in that last decade where the data has been compiled, we have more 100-year events and far more 10-year events than in any preceding decade. So I'm actually going to back up to the previous decade and highlight for you one event that happened in August 2007. So the graph shown here is illustrating how much rain fell during this event. And just kind of call your attention to the blue areas. You know, that's when we get into the 6 inches plus. So it's about a 100-year rainfall event. And in that far southeastern corner of the state, there was actually a record set during this event. And that record still stands for the most precipitation in 24 hours at National Weather Service observing station. And it was more than 15 inches of rain that fell in 24 hours from this event. The gray dots scattered throughout the state here represent bridges. So not only state bridges, but also local bridges. And then you can also see like the road networks. The red stars are locations that were flagged in the hydraulics unit for one reason or another. It might be locations where there's an erosion issue or a scour critical bridge or a spot where we know highways tend to overtop. And so, you know, we look at how much rain fell over a really large area during this event and think about all those assets that were really put to the test during this event. It's not surprising then that we had some damage, right? So the photo on the left is from the Money Creek Bridge on Highway 76. And, you know, during this event, the water in Money Creek really swelled and it ended up washing away the bridge entirely. So of course we've got, you know, maintenance forces out there closing the road to keep the travelers safe. And that closure had to, you know, continue until that bridge could be replaced. And then on the right, we see Highway 74 through Whitewater State Park. And again, there's so much water in the river because of that rainfall event that it led to erosion along the roadway embankment and caused the damage that we see here. So once again, we've got to close the road, keep the public safe, and get the repair completed. And following that event, District 6 put together a really nice map that illustrates really how widespread the highway closures were, you know, and so we've got the purple lines showing the state highway closures. But what you have to keep in mind is that there's also local roads that sustained damage from that event and were closed as well. So we're talking about, you know, really significant impacts to transportation following this flood event. Now, that was almost 20 years ago, but we got a reminder just last summer of how impactful flooding events can be. So this is a screenshot from our 511 map taken last summer. This is around the same time we started to learn about the Rapid Ann Dam getting overtopped. But here we see that there were more than 20 flood-related closures and warnings just in southern Minnesota. And, you know, because of the scale of the map here, you can't even see northeastern Minnesota. But at the same time that we were experiencing these impacts, there were areas in northeastern Minnesota and the Arrowhead region that were also experiencing flooding. And this is a map that shows the rainfall totals from that event. So in that northeastern corner of the state, we're seeing, you know, 5 to 6 inches of rain. Again, that's like a 100-year rainfall event. That's what we would typically size ponds and some bridges to handle. But in southern Minnesota, we got more than 9 inches of rain. And this is over a 9-day period. But that's still on the order of a 500-year event, so far exceeding what we would typically be using in design. All right. So transitioning now, hopefully you have a good understanding of how flooding can affect transportation. So I'm going to talk a bit now about the research project that is underway. So again, the title being Investigating Real Storms and the Impact of Potential Climate Change Adaptations. So one of the tools that our research team at the University of Minnesota is using is a hydrologic and hydraulic model, and I'm going to say H&H model for short. And an H&H model is something that we use every day in water resources to design our water infrastructure, right? Our culverts, bridges, storm sewers, etc. And in order to create an H&H model, we have to first define the rainfall event. So we need to tell the model how much rain fell over what duration and what the rainfall distribution looked like. So was it sprinkling or pouring throughout the duration of the event? We also need to tell the model what the watershed looks like. So how large is it? What does the land cover look like? Is there impervious surfaces like buildings and pavement? Are there pervious areas like lawns and forests and wetlands? And what are the soil types like? We also define the antecedent conditions. What is the soil moisture like prior to the rainfall event that we're simulating? And what we get out of the hydrologic component is really an understanding of how the watershed responds to the rainfall event. How much water from the rainfall event gets absorbed by the soil and how much runs off downstream. And then the hydraulic component of the model helps us understand what that runoff does downstream. We can define ponds, rain gardens, pipes, ditches, streams, other features that are intended to hold or convey the stormwater runoff. And ultimately what we get out of our H&H models is an understanding of flood depths and peak flows. When I'm talking about investigating real storms, I'm going to focus mostly on the distribution. So in our H&H models, we have to tell the model what the rainfall distribution looked like. And this is a really typical rainfall distribution that we apply. And what it's showing is that at the beginning of the event, it starts out as just a sprinkle, and then the intensity kind of gradually picks up. And in the middle of the rainfall event, it is just pouring for 4 hours, and then it starts to taper off again. So with this rainfall distribution, we see 70% of the rainfall occurring in the middle 4 hours of the event. This is a really intense period of the storm, and it is sort of a conservative way of simulating a rainfall event, because we know that in reality, a rainfall distribution might look like this, or this, or this, or this, right? Rarely, if ever, do we have a real rainfall event following the same distribution as what we see in the green line here. And that's what we typically assume for designs. Another way to look at rainfall distribution is from this graph from the June 2012 event. And you guys might remember that this also had widespread damage and impacts to transportation in the Duluth area. And what this graph is showing us is that in the beginning of the rainfall event, it was pretty light, pretty, kind of a sprinkle, maybe pick up a little bit. And then it really got intense, almost 2 inches per hour. And then there was a little bit of a break. And then it got pretty intense again, and a break, and intense, okay, and so on. And what's important to think about here is that when we get these breaks between the really intense periods, it gives the watershed a chance to recover, right? So it gives the soil a chance to sort of drain a bit and have some capacity to absorb more runoff. And then it also gives our ponds a chance to drain out some stormwater to recover some of their storage capacity. So this is a real rainfall distribution with those kind of periods of relief in there in between the really intense times. It's different than what we typically assume in design. When I joined MnDOT 2 years ago, there was already related research underway, and they were really looking at what can we do to reduce our flood risk. And so they were evaluating strategies like adding more stormwater management features to help slow down the water. And they were really focusing on how do these features help us reduce flood depth and peak flow. I encourage you guys to check out that research, but I am going to kind of spoil it here and let you know that a lot of these strategies had really minimal benefit. And what they showed is that with that typical distribution that we assume, most of the water from the rainfall event ended up flowing downstream, and only a portion of it was absorbed either through rain gardens or other pervious areas like lawns. But they suspected that that had a lot to do with how conservative that rainfall distribution was. And so they tested one watershed with a uniform rainfall distribution. So just a steady rain over that 24-hour period. And what they found was that you could really reduce, actually these adaptation strategies were quite effective in reducing that runoff and increasing infiltration capacity. So this again is just a uniform rain, also probably not realistic, but it gave some insights into the effect that our assumed distribution might have on the results that they were seeing in that research. So as I mentioned, when we're building these H&H models, there's rainfall parameters that we have to set. And in the preceding research, they did test changes in rainfall depth corresponding to climate change. But with the current research, they're actually going to take a closer look at these other parameters. They're going to review historical data to see what trends there might be in rainfall intensity and distribution and duration. Then, with those insights, they can reassess our infiltration capacity for pervious areas and green infrastructure like rain gardens. So perhaps, we can count on pervious areas and green infrastructure to help us reduce flood risk. And then they're also going to look at those watershed adaptation strategies again to help us determine, the best place to be investing to help reduce flood risk. So the outcomes of the current research will be a better understanding of the trends in rainfall intensity, duration, and distribution. And the research team is working on that task right now. Then they'll also be using their H&H models to really test those traditional rainfall assumptions, those that we've always used in our designs, versus the lessons they've learned by looking at trends, so versus real storms. And how does the difference in our assumptions affect the timing of rainfall and runoff and ultimately downstream flood risk? And then finally, they'll be looking at flood risk management strategies so that we can get a better understanding of, again, where is that most cost-effective way for us to spend money to help reduce flood risk? So how do we plan to leverage the outcomes? We are in the process of developing new design guidance. It's really focused on making our water resources designs even more resilient to flooding. And so it presents an opportunity for us to then incorporate some of the findings of this research. We also recently introduced something called a check storm. So even though we typically would design for a 10-year or 100-year event, what we're encouraging designers to do is consider a what if scenario. What if you experience an event that exceeds what you usually design for? What are you seeing for flood damage potential? And do you need to make some adjustments to your design to count for that? And so if there are takeaways from the research team about rainfall distributions and intensity and duration, we can also include that in this design guidance. Ultimately, again, we want to make sure that we are prioritizing the best, most effective adaptation strategies. And that is probably the most important takeaway from this research. We know that we're going to have to keep investing to make our infrastructure more resilient to flooding. So we want to get a better understanding of the cost effectiveness of flood resilience strategies based on real rainfall characteristics so that we can make wise investments in flood risk reduction. And that concludes my presentation.
Thank you, Rachel. Thanks to all of our presenters. We do have just a few minutes left for questions. So what questions do you have for our presenters today? You can go ahead and put those in the chat or raise your hand. We'll acknowledge you. Yeah, I think we can provide to Rachel that LRB completed research that you mentioned and any other resources that the speakers would like to share when we share this this webinar recording with the group. And just acknowledging Michael had a good sort of forward-thinking question for Dan in the chat that you answered about costs for connecting to the electric power transmission network. So thanks for answering that. Possibly another research question. Any other questions? Michael, go ahead.
Yeah, Rachel, is the research project intended to collect data primarily from District 6, or is it going to be statewide in scope?
It is statewide in scope. So when they're looking at the trends, trying to identify trends in the rainfall distribution and duration and depth even, that's a statewide effort. We do have some TAP members scattered throughout the state as well. One of them happens to be in the District 6 area.
Thanks. So I want to acknowledge that we're at the end of our scheduled time. So if you have other questions, maybe our presenters can stay on to answer those. But I just wanted to thank everybody for joining us today and hope that you'll join us for our next webinars in our series. Again, we'll follow up with you via email with a link to this recording of the presentations, any resources. So this does conclude our webinar, but again, any questions that you might still have, go ahead and put them in the chat and we'll stick around for a few minutes for those who can stay. Thanks, everybody. Well, great. Thank you so much. I appreciate it. Hi, Bruce. Well, great. So are any of you on technical advisory panels now, besides for these projects? Are these the ones that you're finishing and leading, or do you have others as well?
I'm actually on a TRB research panel that kind of ties into this work as well, where there's a research project that's working on a revenue tool for state DOTs and local agencies to look at as they add fees or different kinds of pricing or possible subsidies for shared mobility and new mobility projects, like what kind of impact that'll have on desired policy outcomes as well as revenue. So it's a slightly different look. This is more about impact on this project's more about impact on infrastructure, accessibility, and greenhouse gas emissions, but they're very complementary. So
yeah, that's great. Bruce, I want to make sure I acknowledge you. If you have a question, go ahead and unmute. Well, wonderful. Thanks to all of you for staying on. It seems like we just have final thank yous and no questions. So thanks for being patient with me as I read my script a couple times.
no problem. Thanks for having us today.
Yeah.
Yeah, thank you, Jackie.
Take care. We'll talk soon. Thanks so much.
Okay. Thanks. Bye-bye.
Bye.
Okay, bye.